Hello, everyone. Good afternoon from Italy. My name is Mario Damasso, and I work for INAF-Astrophysical Observatory of Torino. And today I'm broadcasting from home due to the COVID emergency. So with this talk, we remove from the outskirts of the protoplanetary disks explored with ALMA and direct imaging to the innermost regions accessible with the radial velocity and photometric transit method. Are hot Jupiter are the main focus of our talk, and but are they a common outcome around a few million years old young stars? This is the main question of our talk today. Hundreds of Jupiters have been observed around mature stars, and their frequency has been estimated to be around 1% for sun-like stars. So do Jupiters become hot within a few million years from star's birth? If the answer to this question is yes, the occurrence rate of hot Jupiters could be higher than for mature stars. I mean for young of Jupiters, not taking into account their survival at later stages. Assessing the occurrence rate of Jupiters at the early stages is very important to constrain models of planetary formation, which also depend on the different properties of the formation environments. And the hot Jupiter detection at the very early stages is fundamental also for testing different evolutionary models. Hot Jupiters are believed to have formed far from their star before migrating inwards. However, the physical processes that drive migration are still poorly constrained by observations. In particular, the time scale over which the migration and piling up of Jupiters occur are a crucial information to investigate and to get from observation. Discovering of Jupiters, therefore, around T Tauri stars will be a major observational step, suggesting in particular that type 2 migration, so this migration is occurring at the very early stages of planet formation, is an efficient mechanism in producing the observed of Jupiters. So to provide observational constraints to answer these questions and other, and more in general, to characterize the architecture of planetary systems, to assess the planet occurrence rate around different types of stars, and understanding the origin of the diversity of the multiplanetary system is are among the main objective of the GAPS program and the sequel of the sequel program GAPS-2, which is ongoing since 2012 and makes use of a HARPS-N and JANO spectrograph observations. In particular, within the GAPS-2 program, there is a sub-program all devoted to young objects with the aim of monitoring young and intermediate age stars to look for, especially for hot Jupiters, and with the part of the focus on confirming and retracting and so put under discussion, investigation, the apparent higher frequency of hot Jupiter, of young of Jupiters, as pointed out, for example, recently by the MATIS project. Usually, we try to get at least 50 epochs for each target in order to provide a suitable amount of observations to try to detect planetary signals in radial velocities which are very highly affected by the stellar activity. So one of the Target of GAPS-2 was the young star, the very young star V830 Tau, around which a few years ago the Matisse program detected an odd Jupiter with an orbital period of around 5 days. And this star became a very interesting target for GAPS-2, exactly for the reasons I previously mentioned. Because the detection of this of Jupiter, together with very recent detections announced this year, represent a very important breakthrough because they demonstrated directly that giant planets not only can form very quickly after the star's birth, but can also migrate very efficiently and quickly within the protoplanetary disk. This star, as observed by Matisse, by the way, showed a very high level of activity, more than 10 times the semi-amplitude of the signal of the climate planet. So therefore, due to the challenges offered by this target in terms of the high level of activity, within GAPS, we devoted 2.5 years of observations with HARPS-N, collecting almost 150 radial velocities. As you can see on the left, in the panel on the left, the typical cross-correlation function of the HARPS-N spectra is really deformed by the very high level of activity. On the right panel, you see the radial velocities of V830 Tau as we have extracted from using 3 different radial velocity extraction methods. This was an important part of our work because, as you can see from the scatter in meter per second, almost more than 1 kilometer per second in the case of the CCF-based extraction. So such a very high level of activity, we tried, due to that, we tried to use different methods in order to see if at the extraction level, we could reduce the impact of the activity in the data. So our analysis of the radial velocities are actually analysis of 3 different data sets. And for each of them, we also tried 3 different methods for try to mitigate and to model the activity contribution, and in order to help emerging the planetary signal detected by the Matisse program. So our analysis is try to be as much as comprehensive as possible. So 3 different extraction methods of the radial velocities, 3 different ways of modeling the activity. The activity is clearly dominating the time series of the radial velocities, as you can see from the plot in the left. The rotation period of the star is well known, it's equal a bit less than 3 days. The conclusion from our comprehensive analysis is that each method actually failed in detecting the planet. And even within a Bayesian framework, we could even demonstrate that statistically, the model with containing one planet in a circular orbit is never favored so our data seems not to support the existence of the odd Jupiter. We asked first if our sampling was sufficiently good, and so if the non-detection of the planet could be due to some missing observations. Actually, as you can see from in the panel on the plot on the left, the coverage, the phase coverage of, so our sampling is quite uniform over all the orbit of the planet. So we investigated our non-detection using simple and more sophisticated simulations, so injection retrieval simulation. And our conclusion in both cases is that we basically are not very sensitive to the hot Jupiter climate by the Matisse program. So our conclusion, from even supported from simulation, based on that, we cannot completely rule out the existence of this planet, but actually giving our high precision and high spectra collected with a high precision HARPS-N spectrograph, we couldn't find clearly, and actually we didn't find the signal of the planet. So at least we cannot exclude the planet, but we concluded that there are several doubts about the real existence of it. So going to the more general conclusions, within the framework of assessing the occurrence rate of young hot Jupiters, our study could not confirm the existence of the very young planet V830 Tau B. And our study first so put in doubt the preliminary estimation of the occurrence rate available with the observation, with the discoveries made up to now. So likely, in our opinion, the occurrence rate is lower than actually it is believed. And the second point is that we demonstrated that it's very, very difficult to find out Jupiters around orbiting very young stars with a radial velocity mean, especially when the activity is very high, as in the case of this particular target. We are going up with the follow-up and of other targets. In particular, we shifted our attention on confirming and measuring the masses of the transiting young planets detected by TESS and the Kepler-2. In particular, of some of the targets we have analyzed and we are still analyzing right now, they clearly show that even in presence of transiting of transits, so when the planets are really there because observed with a different technique, by the way, measuring the masses through radial velocities is still a very difficult task to achieve. Thank you for your attention, and stay tuned with more results from the GAPS program to be published in very, very soon.